Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. In this video we're going to be talking about field homomorphisms and isomorphisms. There's going to be a handful of results. I think the thing that you'll see is that the proofs for these are really very short, but they use a lot of the ideas that we developed when we were learning about rings and homomorphisms on rings, and it just comes to applying those specifically to the types of fields that we've been looking at. So let's just review the definition of what a field homomorphism would be. So a field homomorphism is it's basically a ring homomorphism, but between fields. And so if we have K and L are fields, and we'd say that phi is a field homomorphism from K to L, if for all A and B and K, we get that phi of A plus B is equal to phi of A plus phi of B, and the product, phi of the product A times B, will equal the product phi of A times phi of B. So this is just the same definition for ring homomorphisms, but now just applied to fields. So something that we've talked about earlier in the term is that any non-trivial field homomorphism is always going to be one-to-one. And this boils down to the fact that the kernel of a homomorphism has to be an ideal, but fields only have two ideals, the whole field or zero by itself. And so this is basically coming from, if a homomorphism is non-trivial, then let's make this pen a little bit smaller. The kernel of the homomorphism has to just be zero. Okay, for any non-trivial homomorphism, the kernel has to be zero. There is no other ideal other than the whole ring that it could be, other than the whole field that it could be. Okay, and so then that means that if you have an onto homomorphism, that it's automatically an isomorphism, so that it's a bijection between the two fields. Okay, so any onto homomorphism is an isomorphism between the fields. Because it is one-to-one, the domain of a homomorphism is always going to be isomorphic to the image, and so phi, if we have phi going from K to L, then K is always going to be isomorphic to the image of itself. And then last but not least, if we have two fields that are isomorphic, K and L, then if we adjoin, if we look at the polynomial ring over them, then those are going to be isomorphic as well, right? And so if you have some isomorphism phi from K to L, then you can create an isomorphism between the polynomial rings. Let's call that phi prime, going from K adjoin X to L adjoin X. And what this is going to look like is, we'll call it phi of f of x is going to be the image of a polynomial f of x. What it is you just send each of the coefficients through here. So this is going to be phi of c naught plus phi of c1 x plus phi of cn x to the n. So this homomorphism is just sending each of the coefficients to what their images are. Okay, so the first theorem we have is that if we have K as a field and f of x is an irreducible polynomial over in K adjoin x, if alpha 1 and alpha 2 are both roots of f of x, and so if you remember from what we've proven, this right here is equivalent to saying that f of x is the minimal polynomial of alpha 1 and alpha 2, then k adjoin alpha 1 is isomorphic to k adjoin alpha 2. Okay, so the proof of this is very straightforward, and so this uses what we've learned about these simple extensions before, and it's that k adjoin alpha 1 is isomorphic to the polynomial ring modded out by, or quotiented by, the ideal generated by f of x. But this is also isomorphic to k adjoin alpha 2 because they have the same minimal polynomial. And so then by transitivity of isomorphism, k adjoin alpha 1 is isomorphic to k adjoin alpha 2. Okay, so anytime you have two algebraic elements that are roots of the same minimal polynomial, then k adjoin either of those roots, those two fields or those two extensions are both going to be isomorphic to each other, right? And the natural isomorphism between them is sending alpha 1 to alpha 2. So that gives you a natural isomorphism between the two extensions. Okay, so then the next theorem we're going to be talking about is let k and L be fields and let phi from k to L be an isomorphism. Let's let f of x be an irreducible polynomial in k adjoin x and alpha be a root of f of x. And beta is going to be a root of phi of f of x. So remember, this is talking about phi of f of x. As we said a couple slides ago, if f of x is equal to c naught plus c1 x up to c sub n x to the n, and this is in k adjoin x, and then phi of f of x is you just send each of the coefficients through phi. And so this now is a polynomial in L adjoin x. And so this, when we talk about phi of f of x, this is what phi of f of x is. And so we're taking beta to be a root of that. So we have f of alpha equals 0 and phi of f of beta equals 0. Okay, so this is the setup that we have. Then our conclusion is that if we do k adjoin alpha, this is going to be isomorphic to L adjoin beta. Okay, and I think most of the work in this is just understanding exactly what the theorem's saying. Again, the proof of this is going to be very straightforward. And so this is going to come from the fact that, so on the one hand, we have that k adjoin alpha is going to be isomorphic to k adjoin x modded out by f of x. Okay, so I need to convince you that since f of x is irreducible, that its image has to be irreducible as well. And so I'm going to claim that phi of f of x is irreducible in L of x, and this will be by quick contradiction, and so if not, well then we have phi of f of x is equal to, say, g of x times h of x in L of x, and this is a non-trivial factorization. Well then, since phi is an isomorphism, then phi inverse is also an isomorphism, and so then we can apply phi inverse. And we get that f of x would be equal to the product of phi inverse of g of x and times phi inverse of h of x. But since phi inverse is an isomorphism, this would give a non-trivial factorization of f of x. And so that's a contradiction. And so we know then that phi of f of x is irreducible in L adjoin x. And so now let's clean up some space here. Okay, now we have space. So phi of f of x is irreducible in L of x, and so this means that since beta is a root of phi of f of x, then this means that L adjoint beta is isomorphic to L of x modded out by the ideal generated by phi of f of x. And then the last step here is just to note that then k, the polynomials over k modded out by f of x, is going to be isomorphic to L of x modded out by phi of x. And so let's do a quick argument for that. So we know that k adjoin x is isomorphic to L adjoin x, because there's the isomorphism from k to L. And furthermore, the ideal generated by f of x, if we then plug that into phi, right? Well, so this is going to be equal to all of the products of phi times f times g for all g in k adjoin x. And since phi is an isomorphism, it's not difficult to see that this is phi of f times phi of g. Again, this is just stemming from the definition of, I guess really should be calling this phi prime, since I'm talking about the isomorphism between k and L, k adjoin x and L adjoin x. But then, since this is an isomorphism, anything in L adjoin x can be written as an image of something in k. So this is really phi of f times anything, let's call it h, where now h is in L of x. And it's clear that this is phi of f of x, the ideal generated by phi of f of x. And so if these two are, if phi of f of x, the ideal generated by phi of f of x, is the image of the ideal generated by f of x, then from there we can conclude that k modded out by f of x is isomorphic to L modded out by phi of x. So let's write that in. So k adjoint x modded out by f of x is isomorphic to L adjoint x modded out by the ideal generated by phi of f of x, and this is isomorphic to L adjoint beta, and this is isomorphic to k adjoint alpha, and then we have this chain of isomorphisms. So again, by transitivity, k adjoint alpha is isomorphic to L adjoint beta. Okay, so the idea in this is that when you look at simple extensions, that where the alpha, what's generating this algebraic element, it can be sent to roots of, it can be sent to other roots of either the polynomial or the polynomial sent by an isomorphism. And so you can send alpha to other roots of basically the same polynomial or that polynomial sent through an isomorphism. You can generate or you can have isomorphisms between fields that way. Now, the last big theorem here is sort of taking this from the other direction. And so this one will take a little bit of time to parse through exactly what it's saying. Okay, and so the idea here is that we have L over K, and we have L prime over K prime, and we have some homomorphism phi that goes from L to L prime, and we have that K and K prime are isomorphic. Okay. And so we have this phi that's a non-trivial field homomorphism that sends K to K prime. Okay, so phi acting just on K is an isomorphism from K to K prime. Okay, and so that gets us to here. So then the statement of the result then is that if you have some alpha inside of L, so alpha is living somewhere inside L, and it has minimal polynomial f of x, then the question is what happens to phi of A, and the answer is that phi of A, so the image of phi of alpha, the image of alpha has minimal polynomial, which is the image of f of x. So it's the image of the minimal polynomial of f of x. And so wherever the polynomial f of x gets sent to by phi, then alpha is going to be sent to a root of that new polynomial in K prime. Okay, so before we go through the proof of this, I want to go through one main application to this, and one important application that kind of signifies exactly what's going on here. And so I'll put this in as a corollary. So corollary is, really in this corollary, we're just kind of thinking about K and K prime as both being Q. And so that's the simplification here. If you have L is algebraic over Q, and L prime is also algebraic over Q, and you have a homomorphism from phi of L to L prime, then for anything in L, any alpha in L, alpha and phi of alpha, whatever it's sent to, are both going to be roots of the same minimal polynomial over Q. So anytime, if you have any element that's algebraic over Q, and you have some homomorphism, then that element alpha is going to be sent to another root of the same minimal polynomial over Q. Okay, and so we can say that it's the same minimal polynomial here, and that really is boiling down to, and this is a fact that is one of the homework problems, and it's that this homomorphism is not going to change where rational numbers are going to be sent back to the same thing by any homomorphism. So the fancy way of saying that is that any homomorphism from a field over Q is going to fix Q. The elements of Q are going to be sent to the same place. And so that means that minimal polynomials over Q are going to be sent to the same minimal polynomial. Okay, so now let's tackle this. And again, the proof for this is going to be pretty quick. And so the proof is that we have that f of alpha is equal to 0. And so f of alpha, this is C naught plus C1 alpha plus up to C sub n alpha to the n is equal to 0. And so this is saying that the minimal polynomial f of x is C sub 0 plus C sub 1 times x up to there. So now we're going to apply phi to both sides. So phi applied to the whole thing. And so by the properties of homomorphism, we can break this down into phi sub C naught plus phi sub C1 alpha, phi of alpha, plus phi sub C sub n times phi of alpha to the nth power. And this is going to have to equal phi of 0, but 0 is sent to itself. So 0, and we can see right here that this is the coefficients are the coefficients of f sent through phi. So this is phi of f with phi of alpha plugged into it. Okay, and so this is the same thing you would get as if you took the image of f and put in the image of alpha into it. And so this is telling us that phi of alpha is a root of it. And then previously we proved that f would get mapped any homomorphism. If f is irreducible, then the image of it is irreducible as well. And so we get that phi of f is irreducible. It has phi of alpha as a root, and so that means that it is the minimal polynomial for phi of alpha over k prime. Okay, and so really the idea of this is that again, the important fact coming out of this is that through a field homomorphism, any algebraic element is going to be sent to another algebraic element that is then the root of the same minimal polynomial or the minimal polynomial that having gone through phi. Okay, and so let me clear this up and make that clear again. Actually, let's go to the last page. So again, the upshot here is that if alpha has minimal polynomial f of x, then phi of alpha, so the image of alpha has minimal polynomial phi of f of x. And this will be very important for us as we move forward. We're going to be looking at, next we're going to be looking at automorphisms of fields. And so these are isomorphisms from the field to itself. And when we get into thinking about properties that are going to come and stem from that. So that is all for this video. I will see you again soon.